in a lot of real world analysis of data, outside of the normal academic environment, what we do is we have some sort of detection device. We keep track of things as they come in. We keep track of what time they come in, what the state of the system is. Personally, I work with some missile dynamics, right? And we look at the missile and how it flies. At this particular time, it's at this location X, Y, and Z. And this particular time, it's at this location X, Y, and Z. But at the end of the day, the thing we actually keep up with is time. We have those other information, but time is the driver. And that's what we want to talk a little bit about today. So maybe I'll just get into it. Let's take a look at a simple example. I've got an object and I'm at parallel, I'm at some sort of origin, and I throw it at 45 degrees and I want to look how it travels. So classical physics has a really good way of figuring this out. You draw a triangle and you say, all right, well, you threw it, but you didn't throw it straight in the X direction. You threw it a little bit in the Y direction. You threw it about equally. So you draw out the triangle and you figure out if I throw it, if the total speed starts out at 48 feet per second, you know that the X version of that is only 24 square root of 2. So you start out at 24 square root of 2 because you're going to keep throwing. Gravity is not stopping you in the X direction. We don't worry about air resistance. It's just going to keep going forever as long as gravity doesn't drive it into the ground, because gravity isn't affecting it this way. It's only affecting it this way. But in the Y case, you have this slightly more complicated expression because you have gravity dragging it down. You're throwing it. As it goes up, the gravity pulls it, so it's eventually going to beat gravity, and then gravity wins and drives it into the ground. That's what happens here as time goes on. This dominates and drives it to the ground. Why is this important? Well, this is important because what I've done is I've now determined I can figure out what X and Y are without thinking of them at the same time. I don't have to say, oh, well, at this X location, the Y location has to be this. I don't have to think about that. I have to say, at any given time, I can tell you what this location is or what this, because sometimes I don't care about the X location. I only care about the Y location, right? If I'm trying to hit a home run, at some point, I do care about the X location because I'm trying to get over the fence. But if I know that I never get higher, for instance, if I never get higher than the fence the whole time, then it doesn't matter what the X value is. I know it ain't gonna be a home run because I'm line driving it. So that can help you out, and it helps to decouple these. And in real world scenarios, this is super important because, again, time is a thing you care about, and then you can figure out what everything else is. So in this case, we called the t value, which t is really, it could be anything, but it's time. Come on, it's time. It's literally a t. It's called a parameter, and these particular types of equations are called parametric equations. That just means that they are based on a parameter. They're parametric. And what we do is we can take these points and we can draw all the possible points that happen. And what's neat about parametric equations is they are excellent for describing things that aren't actually functions of the two variables you consider. So an example is like a roller coaster. So if I'm riding a little roller coaster and then I do a loop-de-loop, and I'm looking at just a cross section here, I'm just looking at it from the side. Well, clearly y is not a function of x, right? If I'm plotting the xy location, y can't be a function of x because it wouldn't pass the vertical line test. Nonetheless, it's still very important for me to know where I am at any given moment, because that's going to tell me about the stresses. That might actually tell me if I'm trying to do staging of these of the roller coaster where I run multiples at once or something like that. I can know how far along something is at any given time. It's very, very useful. And we just call this what's called a plane curve, where you plot it all. If you do any kind of real world data plotting, you're just going to plot x and y in like a scatter plot, and it's going to generate something like that. But mathematically, we call that a plane curve. And we also plot something called the orientation. What we want to see is over time, because it matters if I'm going this way on the roller coaster versus going that way, especially if there's a car coming along. behind me, right? So, think about it sort of like your commute. Your commute from where you live to work and the commute from where you work to where you live probably is pretty much the same path. Obviously, lanes and whatnot, but if you were, bird's eye view, it's pretty much the same thing. But it matters a lot whether you're going to work or coming home from work. At least it does for me. So that's that. We call that the orientation. The reason we use the word orientation is because it a lot of times it has to do with like how you're moving. If you notice, if you move in clockwise, well, this is clockwise to me, so it's probably not clockwise to you. So if I move clockwise or anti-clock to you, and then I go the other way, I'm technically drawing the same thing, but I'm going in opposite directions. So it matters how I get there. That can tell us something about what the resulting behaviors are, especially when you start to get into vector calculus. If your vector's moving this way, it's going to generate, think like you're screwing a screwdriver. The screwdriver's moving, spinning, but whether you're loosening or tightening matters a lot about how you're spinning, not just where the screwdriver is. And that's the idea. And so anyway, plotting this stuff is actually pretty easy. What you do is, if I have a parametric equation, we don't want to plot this as it'd be kind of nasty to look at the points right here, but it's not terrible, but this is a lot easier. If I have this parameterized equation where x is time plus 3 and y is the time value squared, the way you plot this is you take the t values and you plot them in increasing order, and then you figure out what x is, and then you figure out what y is, and these are the points you plot. So I'll plot 1, 4, 2, 1, 3, 0, 4, 1, 5, 4, 6, 9. And then I draw little arrows because that's the orientation. Now, it's natural for you to think, well, okay, of course the orientation is this way, that's the way the x is going. But it doesn't have to be that way. It could be the other way, depending on how it's graphed. The orientation could actually go backward. So you have to pay attention when you're doing these sorts of things. But ultimately, this is a very powerful tool, and actually there's some interesting calculus that goes along with this that allows you to develop some really rich understandings of what's going on.